So here you have it, a very small and a very simple rotary vane engine prototype, which I made based on the dimensions of the rotor and the vanes of the cheapest impact gun that I could find at the nearest hardware store. I made the CAD for this little design using my new favorite CAD software, Onshape. It's like SolidWorks. In fact, it was created by the founders of SolidWorks, but unlike SolidWorks or Fusion 360 or other modern CAD software, Onshape is built in the cloud and operates in a web browser. For me, this is a very big deal because I often work in CAD and Adobe Premiere Pro at the same time, and then I also record my screen at the same time, so I can put engine animations into Premiere Pro as I'm editing. Despite me having a nice laptop, this often caused my CAD software to crash and I would lose my work, and this is of course frustrating. But because Onshape operates in a web browser, it means that I don't have to strain my hardware and CPU and GPU, and so nothing ever crashes anymore. On top of this, Onshape has all the features you would expect from a modern CAD software. You can use it even on devices that you don't own because you don't need to have anything installed on the device. Onshape also adapts its layout based on what software you're coming from, so there's no annoying learning curve. It enables simultaneous collaboration on projects, and it has a large public library with many different CAD models that you can explore, download, and modify to your liking. Honestly, it's a very potent and streamlined package for anyone that needs CAD software for pretty much anything. And if you want to try it, you can go to onshape.pro/D4A, and you can try Onshape for free for 6 months. Okay, so that was the CAD. Once I was done with the CAD, I had to get all of it made somehow. For that, I turned to JLC PCB. What I like about them is that their prices start super low, just 3 cents for 3D printing and just $8 for CNC machining, which means that you don't need a giant batch of parts or a giant budget to get yourself a prototype of whatever it is that you need. Something else that I really like is that you don't have to wait for a quote. You just upload your file onto the website any time of the day and you will get an instant quote. And if there are problems with your part, someone gets in touch with you quickly and in proper English. All of this has been CNC machined in 7075 aluminum. The front engine cover is transparent acrylic, which I have scratched while unpacking and will never forgive myself for that. And finally, the housing of the engine itself is 3D printed stainless steel. Now, I have quite a bit of experience with CNC machining, especially aluminum, but this is the first time in my life that I'm holding a 3D printed metal part in my hand, and I have to say that I am very impressed. This is nothing like I expected. I expected something flimsy and lightweight, but in fact, this feels like proper metal. It is massive, it is dense, it is heavy. Let me just give you an impression of the weight. This thing feels like a casting rather than a 3D print, so very, very impressed with this. But all of this is just sort of the tip of the iceberg when it comes to the prototyping and manufacturing capabilities of JLC PCB. They work with many other materials, surface finishes, tolerances, you name it. If you want to try them out yourself, there's a link down in the description as well, which you can follow and get a new user coupon of up to $60. So that's how I made it. I have to say that I'm very grateful for living in a day and age where we can get from an idea to an actual part in your hand in a matter of days. And that's because we have versatile and powerful CAD software and rapid prototyping services at normal prices right at our fingertips. 20 years ago, this would be impossible. Not only would it take months, it would actually cost a small fortune. So, very grateful for that. So, as you're probably aware, this video is going to be a follow-up to my previous video on rotary vane engines, where I explained the working principle and the concept of the rotary vane engine. And in this video, I'm going to use this little prototype to answer some of the key questions raised in the previous video. Now, I will try to actually put all of these parts together and start this little engine later in the video, but because I have no idea what's going to happen during the start attempt, this thing might blow up or fall apart, who knows. So while I still have it, I'm going to use it to answer the questions first. Honestly, I'm surprised this question was asked so many times because I thought it was self-explanatory, but apparently it wasn't. It was asked too many times for me to ignore. It's a pretty simple question, simple answer, so let's get it out of the way. This little 3D model that was shown in the previous video is obviously a cross-section of the engine. And while it may seem that the vanes might catch onto the ports in this fully frontal cross-sectional view of the engine, it's also very easy to imagine how the vanes are larger than the ports. If we observe our little model right here, you can see here we have the intake, the exhaust port, and here we have the vane passing by along the ports. The vane is larger than the ports, hence it cannot fit any way into the ports and thus cannot catch onto the ports, do any damage or any of that. That was also shown in the last video. The engine gets rotated. You can see how the port is smaller than the vane. But obviously noticing that takes watching the video before commenting, and that is asking too much. In the last video, I have said how the rotary vane engine is a vibration-free, a perfectly balanced engine. Many commenters responded to this saying how, because the vanes themselves move up and down, they create vibrations, so it's not a vibration-free engine. Well, I'd like to direct your attention to the fact that each vane is opposed by another vane, perfectly opposed in fact. So when one vane is extending from the rotor, so too is the other vane. When one vane is retracting back into the rotor, so too is the other vane, which means that they create forces of equal magnitude but perfectly opposite direction, which means that the forces cancel each other out. The same thing happens in our little prototype where we have 6 vanes instead of 4. Again, the result is the same because here too we have perfectly opposed vanes, which tells us that as long as we have an even number of vanes, we can distribute them on the rotor so that they perfectly oppose each other, leading to 0 vibrations. There was a very high number of comments saying how the springs in a rotary vane engine are a point of failure because they're gonna get weak over time, fatigued or whatever, and they will fail, and when the springs fail, the vanes also won't do their job. Honestly, I have absolutely no idea why there were so many comments around the springs. The springs are not an issue. As you know, we have valve springs in pretty much every 4-stroke engine out there. 99% of them have valve springs. Are they a problem, a common point of failure? No, they're not even a service item. They're not expensive. They last thousands upon thousands of kilometers and hours of operation while being compressed and extended thousands of times per minute. Nowadays, we have the technology to create very cost-effective, yet very durable, very high-quality springs for all sorts of applications. I really have nothing to add to this. In the last video, I have mentioned how centrifugal force flings the vanes outwards, causing them to contact the housing, leading to increased wear and reduced efficiency, especially at high RPM, because the higher the engine speed, the greater the centrifugal force, and thus the greater the force with which the vanes are pushed into the housing. And then, as a theoretical solution, I suggested piezoelectric actuators to prevent vane tip and housing contact and to ensure a no-contact gas seal, which would prevent a leakage between individual vane-created compartments and would also reduce friction, leading to improved efficiency and improved lifespan. Many people responded in the comments saying how piezoelectric actuation cannot be used for this purpose because it can only handle very small motion ranges, a few micrometers, and obviously the vane has a much greater range of motion. Yes, that is correct, but I never said how piezoelectric actuation would handle the entire range of motion of the vane, and that's because it doesn't need to. And that's because centrifugal force already does 99.999% of the work for us. As you can see on our little prototype, as soon as we initiate rotation, centrifugal force immediately flings every vane to the maximum possible point of extension. And that means that as soon as the engine starts rotating, every vane tip is going to be contacting the housing already. So we don't really need to control the entire range of motion. We just want to control the last 0.001% with piezoelectric actuators by either embedding them in the housing or in the vane tips, and then they can create this no contact gas seal. They don't need to control the entire range of motion. But piezoelectric actuation is just one potential solution. There are many other different solutions for vane movement control. For example, in 1967, Popular Mechanics published an article about a 400 horsepower vane engine that used a cam in the center of the rotor to control blade movement. Another example is this system conceived by an inventor from Poland, which incorporates a predetermined track through which vanes and vane guides roll during engine operation. This is a simple system that has the potential to greatly reduce friction and wear. One of my subscribers also sent me this email after I published the last video, where he suggests incorporating gears to control vane movement, which is another viable solution, which was in fact already patented in the past for rotary vane engines. So as you can see, there are many different ways to control vane movement. Of course, which one of these is best suited for what kind of application and budget must be discovered through methodical research and development efforts. Let's imagine a moment when the vane is extended out from the rotor, and then let's imagine combustion pressure acting on it from this side. Obviously, this will try to angle the vane in its slot, and the result is that we get a point of contact here, and this leads to material fatigue and increased wear, which eventually leads to failure. Now, depending on the thickness of the vane and on how much it protrudes outside the rotor, this failure point can be delayed far into the future, but yes, in this simplistic design, the vanes will ultimately fail. But there are ways around this. Allow me to introduce you to this engine. It's a rotary vane engine developed by a company called General Vortex Energy, which received a grant in 2003 from the United States Navy to develop a rotary vane engine. Unfortunately, the only thing we can find about this engine online is this image that you can see here and some text, because as is customary with military projects, everything else is confidential. But as they say, an image is worth 1,000 words. And indeed it is. I would like to direct your attention to these pins at the ends of the vanes. You will also notice such pins in this patent for a rotary vane engine, and this patent was assigned to Samsung, and there's also more pins in a rotary vane engine shown in this patent, which was assigned to Pratt & Whitney. These pins change the point of rotation of the vane from the middle of the vane to the base of the vane, and thus they reduce the number of contact points. But more importantly, they enable vane lubrication too. Here you can see it explained in the Samsung patent. As you can see, by incorporating a guide pin and by keeping rotor internals separate from the combustion area, we can of course lubricate the vanes, which means that we can minimize the negative effects of the forces on the vanes by using a film of oil to absorb such forces. Additionally, a guide pin mechanism with an end plate channel can enable a very easy vane removal and replacement. So this is the problem. Combustion always occurs in the same part of the rotary vane engine, here around the spark plug. Because this part gets the hottest, it leads to uneven engine heating, which leads to uneven engine expansion and ultimately failure. Many have cited the Wankel engine also as an example of this. Combustion always occurs at the same part of the housing, so the housing expands unevenly, again leading to failure. If we observe a conventional reciprocating piston engine, we're going to see that here too we have uneven heating of the block, because combustion here too always occurs at the same spot in the same place. It doesn't just randomly change locations around the engine, hopefully. So that means the top of the engine block gets hotter than the bottom of the engine block, right? And in some designs we even have a non-centrally located spark plug, so one side of the cylinder gets hotter than the other side of the cylinder. Is this a big problem and a source of engine failure? No, because to put it in the simplest terms possible, if we get uneven heating, we are going to implement uneven cooling. This is why we have cooling channels at the top of the engine block and not at the bottom in the crankcase. In the case of the Wankel, this uneven heating of the housing is a pronounced problem, truly pronounced problem, only when we start pushing a pre-designed, pre-existing engine anatomy into levels of heat and power that are outside its intended design and application and boundary, because Mazda designed the 13B platform for the heat of around, let's say, 280, 300 horsepower, not for raw dom levels of horsepower. So of course this becomes an issue. The same goes for a rotary vane. If we expect massive heat, we are going to design our cooling system accordingly. So the more uneven the heating, if we want some big power, big boost, crazy heat, then the heating is going to be very uneven, but we're going to compensate with more uneven cooling. So, as with any engine, we try to predict the intended application as best as possible and prepare for it. So, I hope this manages to at least cover the key questions that have been raised in the comment section of the previous video. Of course, we can't cover everything because they're in one video. There's been a lot of questions, but I hope I managed to address the key questions. So that's enough talking for now. Now let's try to start this little prototype. Okay guys, so here is the setup, and although upon first glance it looks kind of nice, it's actually garbage, because after trying to build a novel engine, although this is a super basic, super simple prototype, there is nothing clever here, I came to the conclusion that boy, have I underestimated this. I may have rebuilt existing engine designs, fixed them. I may have talked about novel engine designs and explained them, but boy, did I never try to build a novel engine, because there's so many things you have to think about, and I forgot some of them. I did prepare for this. I did make a list of things that I have to think about, but I forgot a few things, and
let me explain everything. So this is a little carburetor. It's from a lawnmower, just your basic lawnmower carburetor, nothing special. Here's the throttle, which we are going to, I don't know, operate by hand. This is our throttle stop screw. It adjusts the idle, I guess. Yeah. Here's a spark plug. Spark plug wire goes to a coil. This is an ignition coil from a pit bike. This is the most simple setup in the world, because here in this flywheel, this is also from a lawnmower. It's a magnetic flywheel. Inside that flywheel, there's a magnet. The magnet passes by this, which is a coil. It energizes, and hopefully we get a spark in here. This is a very basic setup. Behind here we have our flywheel, and in the flywheel I have incorporated these notches. Another one where I'm going to put in a pull cord and then pull this to hopefully create spark and get this started. We're going to put a little cup here with alcohol, 96%, I believe 97% alcohol here, and get it then into the carburetor. You just press this bulb and the carburetor is going to suck in the fuel in there. So where I did mess up is number one here. This is the connection between the flywheel and magnetic flywheel and the engine itself. Here I didn't do something right, so I forgot to design a part for this completely, so I used a part from the impact gun and some, as you can see, JB weld, very embarrassing. And then I just used this little thread rod, and then I made a thread in the original aluminum flywheel. I made this thread at the last minute by hand, just so I can make a start attempt, because I cannot leave this and wait more parts and something. I have to try it, although our chances are very slim. So because I made the thread by hand, you can see this is not very centered. Observe, look, it's all wobbly and horrendous. But I tried pulling it once with the pull cord, and you can pull it. So I'm gonna pull it now and see what happens. If the carburetor doesn't pull in fuel, I bought some start spray for actual engines. I'm gonna spray it right in there. I think the spark is our biggest weakness now. Anyway, let's try it and see what happens. Okay, the final thing is the pull cord. I have not tidied up, so the whole place is a mess. I'm walking on tools. See, I haven't thought about this. The pull cord is now interfering with the coil. What a disaster. Oh my god. Okay, it's fine. Oh. Okay, I think the pull cord is way too long, but who cares? Let's just pull it. Okay, ready? Okay, ready? Yeah, nothing. Is the engine even getting fuel in there? Seems like it is.
Okay, something weird happened. The vanes are no longer coming out. Watch, only one extends from the rotor. The rest are stuck. I guess that's why we would put springs in it. But why would they get stuck?
Okay, it seems that the vanes won't retract only because they're wet. And the little layer of alcohol keeps them stuck in the housing. Wow, who would have thought? Yeah, this I could never predict. But of course, that's really not our problem. Our problem is the spark. Let's see if there is ever any spark. Today is not my day. Even the microphone is falling. Okay, I know this was just a first attempt, but even for a first attempt, this was laughable and pathetic. And I give this first attempt a rating of 1 out of 10. Seriously. I hoped for at least one combustion event. The good news is that the insides of the rotor are wet. The inside of the engine is a bit wet. God. Okay, I'm gonna keep the microphone here. The insides of the engine are a bit wet, which means that we do have some vacuum. It's pulling a bit of alcohol in there, a bit of fuel in there. Although I would expect there to be more. There's just a very, very small amount in there. So probably very little vacuum because I didn't seal the front properly. I hope that the very tight fit between the bearing and the shaft is good enough, but I think it's not. But overall, I very much underestimated this. I'm not discouraged. I want to try again. I learned something from this. I learned that I have underestimated it. There needs to be more prep, better prep, many more things taken into account. Although, and also this lawnmower magnet flywheels ignition coil setup is junk. I don't think this is good. I really ruined it with the manual thread making. That was a big mistake. Should have specified that in the CAD. I forgot. So yeah, I will probably try again after I take a big break because this was kind of hectic. Videos like this, I think, have to be made months in advance. Something this complex, because even though it's a simple engine, there's a lot of things around it. It's like a little ecosystem of potential problems. So yeah. If you have ideas for a future attempt of how, or maybe some CAD you want to voluntarily give up. On that note, there was somebody in the comments, I think at the top of the comments in the previous video, who said that he's been doing this for decades with a bunch of different rotary vane engines. Sir, I'd like to say hats off. I did this for like 3 days, worked on this, and I'm exhausted. Seriously. But you get this bug where you want to do it again, like until it starts. And I don't know why. Even if it starts, I have nothing to gain. I don't think I'm going to devote my life to making novel engines. Oh God, I hope I didn't catch some weird engine making bug. And then I'm gonna ruin myself trying to build something that is difficult to build. If you have CAD ideas, I think I can get them made, and maybe we can try something again, or not ever. I don't know. This was an eye-opening episode. That's all I really can clearly see at this moment. Yeah, sorry I didn't give you even a single proper combustion event. I do regret it, but I think it's an important view of reality of the complexity of this stuff. So at least I use this to answer some of the key questions and for a bit of educational value, so it's not all wasted. Yeah, as always, thanks a lot for watching, and I'll be seeing you soon with more fun and not so useful stuff on the D4A channel. Yeah. Ugh. I feel defeated, but I don't want to say I lost the war. This is just one battle. But should I even do more battles? Is this, like Don Quixote fighting windmills? I'm gonna stop talking. Thanks all for watching. See you soon.